Morning, folks. Here we go. So, what you're going to see today is um, we're going to talk through this concept of forces on an incline, basically normal force, force applied, everything like that. All right. So tomorrow you're going to have a quiz. Whoops, this is not going to be closed. Right? So this will be, it'll still be an open note quiz. Sorry. Um, You'll see a sliding problem, you'll see a pushing problem, and then you'll see a forces on it. Okay? I will have sessions available tomorrow to be able to talk through each different type of those. I believe the sliding is at 10 o'clock, the pushing is at 11:10, and the forces on an incline is at 1 o'clock, 12:55. So let me know if you got questions there beforehand or anything like that. Okay. All right. So here we go. So when we look at this stuff here, what we're going to see is we start off kind of general in the sense that if the object on the ground, the way it is, straight into it, right? Straight into the ground. So just like you saw in the graphic on the front slide, where the roller coaster was going, the weight is always trying to push into the surface or basically straight down, so to speak. Okay. Then we start to look at that becomes our normal force, right? The normal force is always perpendicular to the surface, meaning that it forms that nice right angle with that actual surface itself, right? Our weight is always going to be straight down towards the surface, okay? So notice, if we change it on an incline, the weight now is still straight down, but here's the difference in it then. We don't necessarily have that force into the surface, right? Meaning you've probably experienced this before. If you're standing on an incline, say you're standing on a hill, right? Your weight is going to be down in front of you, right? Even though your feet are trying to push into the surface. Now, depending on how steep that angle is, and how fast you're moving, all of a sudden now you've probably experienced it where you go head over toes, right? Where all of a sudden that angle gets to be so steep that you take that step and now all of a sudden that balance or that weight is way out in front of you and your body can't control it anymore and you fall and tumble, right? Um, that's what we're looking at now with this incline, right? So the yellow is the force that our body is trying to push into the actual incline for us, right? So when we look at this normal force now, the normal force is still going to be perpendicular to the surface of it, okay? So our normal force still is going to be acting at a 90-degree angle to the surface. Now, again, whether or not we have enough force to be able to keep our feet planted on there, it depends on the angle. If it's a real shallow angle, like a very shallow hill, one that's very almost flat, the normal force is easy, right? But the steeper it gets, all of a sudden now that normal force becomes less and less and less, and our weight actually getting us pulled down becomes more and more and more, right? So for us, when we look at this, normal force is equal and opposite to mg cosine theta. What I mean by that is this. Down here, yes, that's going to be the weight version of our force, right? Because in actuality, what we're seeing is this thing is going to drive right down there. But this is the actual component of it that is pushing into it, okay? And the way that we get that is that we use that angle with respect to the ground on the front, okay? So when our normal force is going up here, the big deal for us is we want to use this normal force just like we have before, where our gravitational acceleration is 9.8. So that's what I mean by this. That mg cosine theta is going to be whatever your mass is in kilograms times 9.8 times the cosine of that angle in degrees, right? Now, yesterday's lecture and notes and everything like that, and even last week a little bit, when we started getting rid of this cosine of theta, The reason is because everything we did was on a flat surface, right? So please know that now you're going to see an angle. Because you're going to see an angle, it's going to be very explicitly written to the problem. I mean, I'm going to be very, very clear with that part of it, that the angle is this, okay? Applied force now. The applied force is going to be measured as mg sine of theta. So when we look at this, this becomes standing on a hill or resting on a hill with a sled, right? And so then the angle becomes important for us, and then our mass becomes important. So once we know those two things, then we can see how big is that applied force, right? And the applied force is just how much force are we going to have going down the hill, caused by our weight in the angle of the hill. Okay? Now, the friction force, right? So the friction force is still the exact same thing for us. It is still mu times our normal force, or mu mg cosine theta. Now, in this case, it just so happens to be up the backside of, or the opposite direction of the applied force, which should make a whole bunch of sense, right? If the green arrow is the way that we want to go, then the red arrow is just the force that is opposing that, going the opposite direction. Now, please be aware, if you're looking at this right now, some of you might be saying, okay, so why can't it just be mg sine of theta? Well, the reason being is that for us, in this scenario, we're actually getting movement down the incline. Because we're getting movement down the incline, friction isn't strong enough to actually overcome it, right? So when we start to see this whole entire process play out for us, what we'll see is, yes, the mg sine theta is the applied, and that's comparable to the mu mg cosine of the force of friction for us, right? So please just be aware. The most likely scenario is this thing's going to slide down, right? So don't start falling into the trap of, well, hey, on the graphic, it's this. No. The green arrow will usually be larger than the red arrow, okay? It's just in this case, in order to actually fit it on there and show it, we had to draw it at a similar size, okay? So that's our force of friction, which opposes the force of motion, right? We could, if we wanted to, right here, put the applied force, have that be our mg sine of theta, okay? So if the object is on the ramp is stationary, meaning it's not moving, what does this mean about our force of friction as compared to mg sine theta? Well, if it is stationary and not moving, that means it's either equal or greater to it, right? So it's going to be equal and opposite of that. So when we look at that concept, and we'll explain this more as we go farther on, meaning that if we have to overcome that, that's a certain set of circumstances that's going to take place. Now, I don't want you to worry about that now, because what we're going to see is that applied force is always going to likely be bigger than the force of friction. Okay? At least in the problems we're working here. Okay? So let's run an example of it. All right, so we want to calculate, so we got a box, all right, I can't see that. It looks like I'll find it on the next one. That is, so calculate the force between the box and the ramp if the mu is 0.15, right? Calculate the applied force. And then we say, in this problem, what is the force trying to make the box move? That'll be our applied force, basically force of gravity, right? Calculate fun and calculate our acceleration. All right, so here we go. All right. I'm going to fix this. We don't ever assume that it's 9.8. Sorry. Or 10. Okay. So we want to calculate the force on the friction here. So our force of friction is what we're looking for. We know that gravity is 9.8. We know that the mass is 20 kilograms. Our angle here is a 30-degree angle. Okay. So we can look at our force of friction. Our force of friction is going to be mu mg cosine theta, right? That's the part here that's going downwards into the actual, that'll be our weight portion, the yellow, right? So we want to find the equal and opposite part of that, which is our normal force going upwards, right? So when we plug it in, our mu is 0.15, mass is 20, our gravitational acceleration is 9.8, and our angle is 30. Here again, make sure that you're in degrees. No, I think somebody had said to me that it was pre-calc that is using radians. Make sure, please, that you switch it up to degrees, especially for this part of it. Okay? So we find our force of friction is 25.5, meaning that the upward force here, going back this way, is 25.5 newtons. Now, if our applied force is greater than that, we get movement. Okay, so then we'll see that this thing will actually move for us, right? So let's calculate that. So when we ask in this problem, what is the force trying to make the object move? It's actually its weight or its gravity being pulled down, right? So mg sine is going to be the kind of calculation that we can do to make that go, right? So our applied force is going to be that mg sine of theta, right? So we take our 20, which is the mass of it, times 9.8 times the sine of 30. What we end up seeing is that our force applied is 98 newtons. Compared to the 25.5 on the previous slide, should this thing move? Absolutely. It's going to slide down this because the downward force is greater than the up, meaning that the applied force is greater than the friction force, right? So we then want to calculate the fun. Well, here we go back to our big equation that we've talked about so much. Fun is equal to the applied minus the force of friction, right? So it's 98 minus 25.5. We know there's going to be movement. In this case, it's 72.5 newtons of actual movement. That's our force moving down. Okay? To calculate the acceleration, what we're going to see here is that's fun equals ma. So 75 or 72.5 divided by 20 should give us an acceleration of 3.7 meters per second. All right. So this would be like if you look at ski jumpers, right? And I don't know what the angle of the ski jump is, but it would be like them all of a sudden sitting on that, letting go, and then just sliding down, right? Or as a kid, you're on the sled on the hill, and you all of a sudden, your mom or your dad are holding the sled for you as you get onto it, and then you just let you go and you slide down, right? Or you get to that point on the hill on Dodd, and all of a sudden you're just riding your bike down. Okay, all of those would be examples, kind of what we're looking at here. All right. So this is a homework problem. All right. So when we look at this one, part A is the only part of the homework, but the part B and part C, kind of the bottom stuff, I added just to make sure that we saw another one. All right. So we got Fernando, who has a mass of 43 kilograms, slides down a banister, which has a coefficient of friction of 0.2 at his grandparents' house. The banister makes an angle of 35 degrees with the horizontal. First and foremost, we want to know his normal force with the banister. Then we want to find his applied force, right? And then we want to calculate the acceleration going down the banister. Okay? So there's our graphic that will help us to solve this thing, right? Again, you probably want to draw that so that you have that in your notes so that it's easy to get to. So we're going to go normal force equals mg cosine of theta. So 43 times 9.8 times the cosine of 35. Plug it all into your calculator. You get 345.2. Okay? That's our first part. The applied force is just going to be mg sine of theta. So when we see the mg sine of theta, that's 43 times 9.8 times the sine of 35. That equals 241.7 newtons. Now, you may be looking at this and saying, okay, this thing's not going to move. Well, hold on a second. We don't know that yet. Yes, our applied force is roughly 242 newtons, but the normal force doesn't tell us anything about movement because the normal force is going perpendicular to or 90-degree angles away from the actual applied force. Until we find the force of friction, we don't know if this thing's going to move yet or not. Okay? Now, side note, likely it's going to move. Okay? So, in order for us to find out that and find the acceleration, we got to find our fun first. Well, we have the applied, but we don't have our force of friction, right? So notice what I just did there. I took our force of friction at the bottom, and I changed it into what we're actually going to need to calculate. So it's going to be 0.2 times our normal force up here. So we'll take this applied force, and then we'll use our 0.2 up above, which is our coefficient of friction, and this 345. All right. So once we do that, we see, okay, 241.7 minus 0.2 times 345.2. That ends up equaling about 173 newtons of unbalanced force. This thing is going to move down the slope, down the banister. Okay? So once we know that, to find acceleration is pretty straightforward, right? We know the fun. Then what we're able to do is say, okay, Fernando has a mass of 43 kilograms. So 172.7 divided by 43, our acceleration ends up being 4.02 meters per second squared. All right. Now what I want you to do is I'm going to encourage you here to hop into section 3 and start running some of those problems as well. So over the course of today and kind of the beginning part of tomorrow, if you're able to look at section 2 and section 3, even if you just watch videos or look over answer keys, that will help you to prep and be ready for the quiz tomorrow. Okay? All right. Talk to you. Bye.